Hi guys, this is Jerry again, doing lecture 5. So the rustling there at the start is me just sitting down, so don't be disturbed. Today I just want to continue what we did yesterday about summarizing matrices. Remember I was telling you that the problem with matrices sometimes is that they're very, very big, and you want to condense the information in a matrix into a single number, because we love single numbers because we're humans. And so if you look at, I'm just going to do a couple of examples here. There's 3 examples I want to talk about. Again, we're dealing with either row vectors or column vectors, and we're going to be dealing with square matrices exclusively in this part. Okay, that's the way it works. This stuff only works for row matrices or column matrices or square matrices. Now, if you have a collection of 3 numbers like x here or y here, it doesn't really matter which way you represent it. You can represent it either as a row or a column. And usually, almost always, the choice is up to you. Whichever way you want to represent that collection of 3 numbers. Okay, so you can represent it as a row, or you can represent it as a column, and that's fine. But even if you look at these 2 vectors here, which are very, very, this is a row vector and this is a column vector, you see there's only 3 numbers here, but you could have a row vector or a column vector which is 10,000 entries. And really what you want to do sometimes is you want to kind of get an idea as to what a typical number in those vectors is. And similarly here for the vector A here. Okay, and again, now I'm going to be dealing exclusively with 3 by 3, but you can do this for 2 by 2, you can do it by 4 by 4 by 4. You get the idea. It's the same kind of idea carries over no matter what the dimension of the matrix is. But if you look at the matrix A here, sometimes you would like maybe just to, and we talked about this yesterday about a square matrix, about how you can get the trace and you can get the determinant. They're 2 very, very important ideas. And today I want to introduce a 3rd idea. Let me just say it now, and so that it sinks into your brains. This idea of what's called a quadratic form. Now, this stuff is not in the book. Okay, so this is kind of a little added bonus for attending DCU. But this stuff that we're going to be doing today is kind of important because you will see it elsewhere, and it should be in the book, but it's not. So basically, I'm saying that I'm just that much better than the 4 guys who wrote the book, basically. Yeah, because I'm so good. All right. So let's look at the row vectors first, and let me just look at I'm going to be looking at x. And as I say to you folks, we want to kind of take okay, in this case it's 3 numbers, but it could be 10,000 numbers, it could be 40,000 numbers. But what we want to do is we want to condense those 3 numbers in this case into a single number. And the way you do it is you get what's called the inner product of the matrix. Okay, so or the inner product of the vector. So let me just talk to you about vector inner products then. And this is just matrix multiplication, and that's all it is. Do not be scared by the stupid terminology associated with it, right? So let me just look at the vector x first. So x, we say, so I want to get what's called the inner product of a vector. Now, the words inner product are very important because that's telling you I want a single number. So this is telling you here a number. That's what I want. I can't spell number. That's a B here, and that's an E, and that's an R, I swear. So an inner product means a number. Okay, so if we look at the vector x, we see it's 1, 3, 2. And the dimensions of x are 1 by 3. Okay, so it's 1 row, 3 columns. Now we want to scrunch, or we want to condense those 3 numbers into 1 number. And the way we do it then is because we know that we want to get a single number, we want to multiply the vector x, 1, 3, 2, by another matrix whose dimension is 3 by 1. Okay, because if we can find another vector whose dimension is 3 by 1, we know that these 2 things are the same, and we know on the outside then we get a 1 by 1, and a 1 by 1 matrix is just a number without any square brackets. And the way you do it, folks, is the obvious one here. Well, it's not obvious actually, but the way that people do it is to get the inner product. Let me call it IP. In this case, we know we have x. Oh, we get x. That's just nothing. Sorry. We multiply x by x transpose. So let me just do this. That's 1, 3, 2. And X transpose is 1, 3, 2. This is 1 by 3. This is 3 by 1. So when we multiply it out, we're going to get a number. And the way you do it, of course, is it's very simple. It's 1 by 1 plus, so it's the row by the column. So the row by the column, 1 by 1, 3 by 3, plus 2 by 2, which is 14. And that's it. Now, guys, in the exam, I won't ask you for, what's the inner product of this vector x. I would tell you calculate x transpose. Okay? Now, when I was doing this the first time, when I first started messing about this years ago, like yourselves, I was always getting confused between this inner product idea of multiplying a matrix by its transpose. But the order comes because we're representing x as a row. So it's 1 by 3. We must multiply by 3 by 1. So that means you have the inner product in this case is x transpose. If you look at y, remember y was 406. So y, in this case, folks, there's 3 rows, 1 column. It's a 3 by 1. So if we want to get the inner product of y, we want to multiply that by a 1 by 3 matrix, because these two numbers are the same, and then we get 1 by 1. And if you look at y is 406. It's a 3 by 1. Y transpose is exactly what we want, because y transpose, the dimensions of y transpose are 1 by 3. So y transpose, folks, is 406 and 406, and you multiply the row by the column, and you get 4 by 4 plus 0 by 0 plus 6 by 6, which is 36 plus 16. Is that 52? Could be. You would see, folks, the inner product is always going to be positive. That's an important little idea, but we're not worried about this. So let me just contrast the two things. If you have a column vector, the inner product is just y transpose y. If you have a row vector, the inner product is x transpose. And believe it or not, I found this very difficult to get my head around, but sometimes it's x transpose, sometimes it's y transpose, and you say, why? It's what you start out, it's what you're representing the three numbers as. If you represent the three numbers, in this case, as a row, then the inner product is x transpose. If you represent the three numbers as a column, then the inner product is y transpose y. Now, folks, don't worry about this. Okay, in the exam, I will give you a vector y and ask you for y transpose y, and if you do that, then you get this. Now, be a little bit careful though, because sometimes, just stupidly, because I don't know, I just get these kind of flights of fancy. If instead of in this case, let's look at the y vector 406. Instead of writing it as instead of asking you to get y transpose y, suppose I asked you to get y transpose. Now, what is that? Well, we know that y is a 3 by 1. We know that y transpose is a 1 by 3. So these two numbers are the same. So y transpose is a 3 by 3 square matrix. So there's a big difference between y transpose y, which gives you a scalar, a number, and y transpose, which gives you a square matrix. Now, you're all thoroughly confused, but just to be careful. Just be careful with this. Okay, the dimensions are very important in a matrix, and especially in matrix multiplication, because the dimensions tell you what you're going to get when you do the multiplication. So I'm just going to do this, in this case now, I'm going to do the y transpose just for the sheer hell of it. Okay, so I'm going to get y transpose on the next page. So y transpose, y is 406. And y transpose is 406. We know it's a 3 by 3 matrix, so that's what I write it down here. And because it's a 3 by 3, I have 3 columns. And that noise is not anything mechanical in me. It's the coffee machine. All right, so that's just what it is. And the coffee machine is just doing something stupid. All right. Now, folks, this is a very kind of strange looking matrix multiplication. And what you do again, folks, to get the first column of the product matrix, you look at the first column of your second matrix. And to get the first entry here is going to be 4 by 4. That's it. The next entry is going to be 0 by 4, and the last entry is going to be 6 by 4. Okay, so to get the first column of your product matrix, you look at the first column of the second matrix that you're multiplying. So as I say, the first one here is 4 by 4. The second one is 0 by 4. And the last one is 6 by 4. Okay? To get the second column of your product matrix, you look at the second column of the second matrix that you're multiplying, and you multiply each row by that column. So this entry here is going to be 4 by 0 up here. This entry here is going to be 0 by 0, and the last one is going to be 6 by 0. So if you do that, you're going to get 4 by 0, you're going to get 0 by 0, and you're going to get 6 by 0. And finally, folks, then to get the last column here, the last column here in your product matrix, you look at the last column here, which is 6, and you multiply each of the elements here by 6. So you get 4 by 6 here, and you get 0 by 6 here, and you get 6 by 6 here. So finally, what you get is you get 16, you get 0, you get 24, you get 0, you get 0, you get 0, you get 24, you get 0, and you get 36. Now, if you look at this, now this is kind of like, does this happen often? Do you often multiply y transpose? No. In practice, this very rarely happens, but you can do it. And you will notice here, guys, that if you look, this is the main diagonal. And if you look off the main diagonal, you get kind of a mirror image here. So this is equal to this is equal to this is equal to this. This matrix here is symmetric. Remember we talked about symmetric matrices? Okay. Now, is this important for your engineering future? No, it's not really important. The other one that we talked about, the y transpose, though, is much more important. Okay, that's the one we just did. Okay, so the y transpose is important. You get a single number. The other one then that you get here is y transpose y. Excuse me, I'm useless. I just go back to bed and just sleep. All right, the y transpose y is the important one because what you end up with is just a scalar or a number. Okay, the y transpose one that we've just done here is you can do it to impress your friends at parties, but that's basically it. It's not really that important, to be honest. Okay, but nonetheless, I could ask you to do this in the exam because sometimes I just forget who I am, where I am, and I do something stupid and I put a stupid question in the exam. And this is an example of a stupid question. But you can do it. It makes sense. You can do y transpose. Okay. So that's how you condense rows or vector matrices, either row matrix or a column matrix. And now what I want to talk about next is condensing a square matrix. How would you do that? So let me just look at the example that we're going to be using. I'm going to use the matrix here, A, which is 4, 2, 1, minus 1, minus 1, minus 2, 3, 0, 0. You can see it. And you can see that matrix here. And the way you do this, the way you kind of condense this matrix is a little bit different. Okay, you don't multiply A by itself because you want to get a single number. What's done actually is you multiply A by columns and rows, vectors. Okay, so I'm going to show you in a second what you do. Okay, so this is remember yesterday. Now this is an important idea of condensing what's in a matrix into a single number. The trace, which is just 4 minus 1 and 0, you add those three elements. The other one then is the determinant of A. Remember we talked about doing this determinant of A yesterday, and this is the last way we're going to be doing it, and it's called getting a quadratic form. So this is very stupid terminology, and it sounds very grand, but yeah, it is kind of important. You might see this as you're going through your engineering studies and wonder what the hell is going on here. And all that's going on is matrix multiplication. And it looks really complicated, but it's not. All right, it really isn't. It's just matrix multiplication. And if you hold your head and you be confident and be yourself, you can do this. It's actually not too bad. Okay, so let me just talk about A here. A is 4, 2, 1, minus 1, minus 1, minus 2, and 3, 0, 0. So this is the matrix A. Now, if you look back here at the matrices, I want to use either X or Y to condense this matrix here into a single number. Now, why am I doing this? Because people have been doing this for years, and they found out this is a very useful way of representing physical systems, actually, what's going on in the physical system, in an engineering system. But from your perspective, folks, you don't care about that. All you care about is getting the answer and doing the following the recipe. Okay. Now, A is a 3 by 3 matrix. Now, if I want, if you look at Y here, Y is a 3 by 1, which is cool. So if I multiply A by Y, I'm going to get a 3 by 1. And then if I multiply AY by Y transpose, which is a 1 by 3, this is the, so you get all these cancellations, you end up with a 1 by 1 matrix, which is a single number. Okay, so if I do this complicated looking matrix multiplication, Y transpose AY, I always end up with a single number. And Y transpose AY, this mess here, this complicated matrix multiplication is called a quadratic. I can't spell quadratic, I can form. Okay. Now, do you have to remember this? No, you don't. What a quadratic form is. But I might ask you to do this kind of calculation in an exam. And what you're doing is you're calculating what's called a quadratic form. Now, I might say, calculate the quadratic form Y transpose AY if A is this and Y is this. That's all you have to, that's it. And so all you have to do is hold your heads and do the stupid multiplication. And you have to remember, though, that, folks, that Y transpose AY is 2 matrix multiplications in disguise. And what you do is, usually you do this multiplication here first. You do the AY first, and you do that calculation, and then you multiply that by the Y transpose. So I'm going to do this for you now and show you how easy this actually is. I know this is when I did this the first time myself, I was not happy. I wasn't a happy camper, but actually it's actually not too bad. It really is. It's just practice. You just look at this stuff. You say, oh yeah, okay, that's that stupid thing that it's this Y transpose AY is 2 matrix multiplications in disguise, and I end up with a single number. That's the important bit. Okay, so let me just do it for you. So the first thing you do, we know we're going to multiply this by Y, which is 406. 40 minus 6, and I'm going to multiply here by 40 minus 6 here, because 40 minus 6 is Y transpose. Now I'm going to do this matrix multiplication first. Now this is a 3 by 3, this is a 3 by 1, so I'm going to get a 3 by 1, I'm going to get another column, because when you multiply a square matrix by a column, you get another column. Okay, that's not obvious when you first start doing it, but it's always true. So a square matrix by a column gives you another column. And what you do then is you multiply the numbers here. So it's 4 by 4 plus 2 by 0 plus 1 by minus 6. Okay, so this is just this multiplication here now. I'm multiplying A by Y. The next one then is minus 1 by 4 plus minus 1 by 0 plus minus 2 by minus 6. And the last one then is 3 by 4 plus 0 by 0 plus 0 by minus 6. And when you do that calculation there, folks, I think you get 16 minus 6, which is 10. You get minus 4 plus 12, which is 8. And the last one then is 12 plus 0, which is 12. Okay, so you get 10, 8, 12 as your result from multiplying A by Y. And then what you must do is you must multiply this baby by this baby. So you multiply 406 by 10, 8, 12, and you get 4 by 10 plus 0 by 8 plus minus 6 by 12. And you get 40 minus 72, which is minus 32. Okay? So that's what you get. Boom, boom. So do not be intimidated by this. And there'll probably be marks for something like this in the exam, if there is an exam, because God knows if we're all still here. This could be all for nothing, folks. We could all be doomed. Who knows? But if this comes up in the exam, something like this, hold your heads. It is actually very, very easy. Okay? Now, another thing I could ask you, though, guys, is instead of Y transpose AY, getting what's called a quadratic form, I could ask you, because if you look back on the original three matrices that I gave you, if you look at X and Y and A, I can multiply A by Y, which I've done here, and I can multiply that product then by 1, 3, 2. So what I could ask you also, instead of asking you for y transpose AY, I could also ask you for x AY. Because x, as we know, is a 1 by 3. This is a 3 by 3. This is a 3 by 1. So these will cancel this will cancel this. So these are the same. So what I end up with is a 1 by 1 matrix. So if I multiply x by a and a by y and result by y, I'm going to get a scalar number. I'm just going to get a scalar, a number, a 1 by 1 matrix, which is okay. Now, because x and y are different, if you look back on what we talked about a quadratic form here, we have a y here and we've got a y transpose here. This is called a quadratic form. Because these two letters here are different, this is x and this is y, this is no longer a quadratic form. This is what's called a bilinear form. Okay? So this is called a bilinear form. And again, you don't care about the terminology. It's just stupid, all right? But I might ask you, in my instance, I might ask you, calculate the following bilinear form, x, a, y, and don't be intimidated by the stupid language. All it is matrix multiplication. That's all it is. And it's two matrix multiplications. You do this one here on the right first, and then you multiply by x. Now, we've already done AY. We found that AY, if you remember back here, was 10, 0, 12, or 10, 8, 12. And if I multiply then x by AY, I get 1, 3, 2 by 10, 8, 12. And what I end up with then is a number, okay? Again, is a number. So it's 1 by 10 plus 3 by 8 plus 2 by 12. So when you do that, sorry, let me come up here. And when you do that, then you get 10 plus 24 plus 24. That's 40, so that's 58, I think. Okay. So this is another, so as I say, guys, the reason why you're doing this is you're taking a square matrix. Let's go back to the previous page, square matrix, and you're condensing the information some way into a single number. And in this case, we got minus 32. And you might wonder, well, what's that telling you? Well, we're not going to go into that really. Actually, what this tells you, this kind of quadratic form, what a quadratic form tells you sometimes is how much energy is in a system, in an engineering system. But we don't care about that. Okay? So, and this is what's called a quadratic form. Do not be put off by the stupid terminology. If instead of y transpose, we have an x, a different vector here, instead of y transpose, it becomes what's called a bilinear form. Do not be put off by the stupid terminology. But you get the same thing. You're always going to get a number. Okay? So when you pre-multiply a square matrix by a vector and you post-multiply it by another column, you're going to get a scalar. You're going to get a number. And that's really, really important in engineering analysis. Okay? Because you come across this a lot. Now, I do this in my stupid research that I do that nobody cares about, as I said to you before. Not even my family care about this. And this idea of quadratic forms is important, actually. It represents, when I'm doing some stupid calculation, it represents the energy of a system. And sometimes then I have to calculate a bilinear form, which gives me something else, not quite the energy, it's something else, but it doesn't really matter what it is. When I was your age, I was very, very hesitant about this. I did not go for this at all because I wasn't really comfortable with what they are. Because I was, what is it really? Don't worry about what is it really. What it is a matrix multiplication. That's all it is. Now, I put some questions on loop dealing with this stuff, and I want you to do them. I put the answers there as well, and hopefully they make sense. Okay. Now I want to do one more thing because again, this is we just dealt with numbers here, and you can generalize this. Instead of having numbers here, you could have symbols, but it's exactly the same thing. And let me just show you. Let me just do one more thing, and then we'll stop. Okay. Is that okay, Finton? Just one more thing, Finton. That's all we're going to do. All right. I know that you're tired now at this stage, but we're gonna push on and finish this, and we'll take a break then. Okay. All right, so let's look at this. Let's look at matrix A. Let me call it cos theta, sine theta, minus sine theta, cos theta. And we'll let x equal to lambda 1 squared, lambda 2 squared. Now, again, when I was your age, folks, I was very, very unhappy with this because I could do this kind of stuff with numbers. Yeah, and then when you went a little bit more abstract and started dealing with symbols, I was always a little bit unhappy about this. But this is fine. Don't worry about this. This is exactly the same nonsense, okay? Now, in this case, because x is a row vector, what you do to calculate the quadratic form here, in this case, is I need to have a column vector here and a row here. So I'm going to calculate x, a, x transpose. That's what I'm going to do. Okay, because x transpose gives me a column, and I like to have in columns here because a square matrix by a column gives me a column, and then when I multiply by x, I'm going to get a single number. Okay, because if you look at this, this is a 1 by 2, this is a 2 by 2, this is a 2 by 1. So when I end up, this cancels with this cancels with this, and what I end up with is a 1 by 1. Okay, there are two matrix multiplications going on here. Let's do this one first. Now you can do it the other way as well. You can do the x by a if you want, and then multiply x transpose, but traditionally you do this one. Usually people do the right-hand side one first. So let me multiply a by x transpose. So what I'm going to, that matrix multiplication here is cos theta, sine theta, minus sine theta, cos theta, by lambda 1 squared, lambda 2 squared. And when I do that, I'm going to get cos theta by lambda 1 squared plus lambda 2 squared sine theta. Okay, it doesn't matter what it is. You can call it, if this was sheep and this was cat, it would be cos theta by sheep plus sine theta by cat. It doesn't matter what the symbols are. Okay, so this is just a test of your understanding of the mechanics of matrix multiplication. That's all this is. On the second row here, you get minus sine theta, lambda 1 squared, plus cos theta, lambda 2 squared. Okay? So then, folks, so that's a x transpose. And then what I must do that then, folks, so then that's equal to that. And I'm going to multiply that then by lambda 1 squared, lambda 2 squared. Okay? So what you do is you multiply this one by this, and and add them together. So what you end up with is lambda 1 squared into lambda 1 squared cos squared theta plus lambda 2 squared sine squared theta plus lambda 2 squared into minus sine theta lambda 1 squared plus cos squared theta lambda 2 squared. Now, guys, you will notice here that this term here, when I multiply in by lambda 1 squared, I have a lambda 1 squared, lambda 2 squared, sine squared. And here I'm going to get a lambda 1 squared, lambda 2 squared minus sine theta. Oh, this should be just cos and sine. Sorry. There's no square there, right? It's the lambda 1 is the squared. Okay. So this is cos theta and sine theta. You will notice here, folks, this is lambda 1 squared, lambda 2 squared, sine theta. And this is minus lambda 1 squared, lambda 2 squared, sine theta. And this will cancel with this. There is nothing sweeter in life than cancellation. Okay, and this should be cos theta as well, sorry. Okay, so this term cancels with this, and what I end up with then is I'll end up with lambda 1 to the power 4 cos theta plus, when I multiply in here, I get lambda 2 to the power 4 sine theta. Now, what does this mean? It means nothing, all right? What is this nonsense? It's just nothing. All this is an exercise in matrix multiplication. And to get into second year, where I can torture you further, and then if you even get to third year, where I torture you even more, you have to do this stuff. And it's very important that you jump on this now, because you will be seeing this as you go through your engineering studies. Matrix multiplication, what's called manipulating matrices in mathematics is called linear algebra. And linear algebra is probably the most important part of engineering mathematics. It really is, because this is how engineering systems are simulated on computers. You use matrices. You know, all those games that you play. My son plays Fortnite, and these amazing realistic shooter games, they all rely on matrices to actually to render the graphics. So whenever you turn or you advance in these games, what's happening is that you're doing matrix multiplication. You're doing matrix multiplication, loads of matrix multiplication very, very quickly. And that enables you to do the actual play the game. So this stuff is becoming very, very important. And you need to get onto this and love it and make it your friend. Okay? And we talked about this in class, how maybe you need a friend. All right? So make this your friend. When I was your age, I had no friends, and I made this my friend. And now look at me. All right. I'll put up another lecture tomorrow. And stay safe. All right. Keep your distance from each other. And we'll talk again tomorrow. Okay? Oh, yeah, tomorrow's lecture is very important. Okay, it's lecture 6. It's called Calculating Inverses of Matrices, which is probably the most important calculation on matrices that you do. Okay, so a little bit of a cliffhanger there to get you to come back. All right, talk to you tomorrow, guys. Bye.